there's a feedback. Okay, just make sure that your mic is there, is on mute. So, okay. Okay, so before we start our lecture, this is just a survey for this class. So let me just move here. So okay, so let's have another survey. And again, this is it's not going to be or it's not yet final, but in case we opt to have the exams in person, would you be able to come to the campus? And this is just a question that we were asked by the admin. For example, they're checking if the students are around the campus or not, and we just want to check the percentages right now if it's a possibility. So I'm going to wait for 1 or 2 minutes. And I know some of you might be attending from a different province or different city, so that's okay. And thanks for sending the link to the poll. And I think that's Ricardo, but yeah, thanks for sending that. Okay. And eventually it will become full because I think I'm only allowed to have 40 respondents. So yeah. Okay, so around 60 or 70, 30 around that. So I'm just checking. Oh, it's full right now, so around 70-30. So my guess is kind of correct. So yeah, this is just I just want to take some data because again, we were asked to just do some surveys in order for us to know who can come, who cannot. So, but again, we're going to make some arrangements for everyone in case it will be the system this term, but maybe not. But we'll see. Anyway, so let's go back to our topic, which is transformations of stress and strain, and I assume that you already have a little bit of discussion about this in Mechanics of Materials 1. For 2, we are going to dig a little bit deeper. For example, I'm going to show you how the equations were derived, moving from 2D, and then we move to 3-dimensional. And then it's not just about stress. We can also use the concept of strain. So for this topic, which is transformation of stress and strain, we have the following objectives. So this is chapter 7 of our reference book. So the first one is to apply stress transformation equations to plane stress situations to determine any stress component at a point. So let's say if we apply a stress to a certain material or component, we pick a point and we analyze what are the stresses involved. And in this particular case, this is plane stress, which means that if we have a 3-dimensional axis, one of the stresses are only applicable to 2 different directions. Now, the second one is to apply the alternative Mohr circle approach to perform plane stress transformation. So take note, 1 and 2, they both refer to 2-dimensional analysis. So it's just plane stress situation. The first one is using equations. The second one right here is using Mohr circle, which I assume you were introduced to Mohr circle. So the third one would be use transformation techniques to identify key components of stress, such as principal stresses. So we are going to discuss more about the key components, what are the important numbers when we are performing transformation of stress or strain. And then the fourth item here is to extend Mohr circle analysis to extend or to examine 3-dimensional states of stress. So you can see the first 3 is 2-dimensional. The fourth one is applying it in the 3-dimensional state. And the fifth one is examine theories of failure for ductile and brittle materials. And this is important if you're going to design, for example, a component. So once you have a component, you apply a load. Will the load fail by means of ductile or brittle manner? Of course, it depends on the mechanical properties of the material. And going back to my example last time, if you have aluminum and steel, of course, they're going to have a different mechanical response. Now, the sixth item here is analyze plane stress states in thin walled pressure vessels. So this is more on the application side. So how can we apply a transformation of stress and strain in terms of actual application? And in this case, it could be applied in pressure vessels. You can also apply it, for example, in oil and gas industry, wherein they use pipeline to transport gas from one location to another. And the final item here is to extend Mohr circle analysis to examine the transformation of strain. Now, Mohr circle is mainly used in stress, but we can also use it in terms of strain, which we are going to discuss later on. So instead of plotting stresses or principal stresses, for example, we are going to plot principal strains. Okay, and for this lecture, in the next few lectures, we are going to focus more on items 1 and 3, which are stress transformation equations and the key components such as principal stresses. Okay, so now let's take a look at the general state of stress when we have, for example, if we have a component, we load it, we pick a certain point, and we try to draw the state of stress in three-dimensional state. So I'm going to write it here. So, okay. So let's say that would be your, so we can call it kind of element. But so we have different axes here. So let's say this is X, this is, let's say, Y and Z. Of course, that could interchange. That's okay. In my case, I think Z is facing towards me. So when we have this general 3D state, so as you know, we have normal stress. So the stress is applied perpendicular to your area. And let's say we can call it sigma X. We can also call this one as sigma XX, which we are going to discuss the naming convention for stress. Now, we can also apply different stress in different direction. So this is sigma Y, or we can also call it sigma YY. And at the top, we can also say that this is sigma Z or sigma ZZ. So for formal naming convention, usually we use two different letters right there, and what those letters mean. So our normal stress or our sigma, so let's go, for example, our example here is sigma XX. Your X, so the first X is described by, sorry. So this would be the direction of normal to the plane. So we have to check what would be the normal direction to the plane. In this case, the plane is, for example, this face right here or this face right here. So that's our face. And once we draw a normal direction, it's parallel to our X. So that's why it's called X. The second convention there is the direction of action, which is the direction of your stress. So in this case, the area has a normal to the X, and the direction of that stress is also parallel to our X. But in terms of book, we normally just use sigma X instead of sigma XX, but in reality, there should be two right there. Okay, just want to check if there's any message. And if you have any message, just let me know. Sometimes I will not notice if there's a message. Just feel free to interrupt me if you have any questions. So now that's the concept for normal stress. Now for shear stress, which is denoted by tau, so it's the same thing. So if we're going to go back to the slides, I'm not going to draw it here because I think it's a little bit small, so I'm checking my video. So that would be tau xy, tau yx, tau yz, tau zy right here, and then tau zx, and this is tau xz. Now, if you're confused how those letters were derived, we have to look again to our naming convention here. So the first letter means something. It's about the plane. So for example, let's take this tau xy as an example. So your tau xy yx, so your y, so that would be related to the plane or the area where the stress is applied. So this would be this area here. Let's change it to pen. So this would be related to this area. So we're talking about tau yx. So so y, so that's the area. What's the normal to that area? That's y. So that's applied along y plane. and then x is the direction of your stress. In this case, this is directed towards x, so that's why that's tau yx. So if we're going to write it here, so that's tau xy. So your x, again, this is the direction of normal to the plane. And again, your y would be your direction of action. And of course, the tau right here would be the magnitude. So, okay, magnitude of stress. So you have the magnitude, you have the plane, and then you have the direction of action or direction of stress. Now, if we're going to summarize what are the different stress that we see in a general 3D state, so just going to, yeah, I can still write here. So we can have normal stress, we can have shear stresses. So for normal stress, we have sigma x. So we have, oops, where's my, okay. So we have x, y, and z. So we can have sigma x, sigma y, and sigma z, or we can call it x, x, y, y, and z, z. That's the same thing. And we have shear stresses. So for shear stresses, we have, just checking if I can still see it. Okay, tau xy, tau yz, and tau zx. So we have a total of 6 different components. I think you may not be able to see it. I'm just looking at my video. But so that's tau xy, tau yz, and tau zx. So we have 6 different components, 3 different normal stress, 3 different shear. Now the question here is why I have 3. If I count here, I have 6 different shears. It's because some of them are equal. So I'm going to flip this one, next page. So it's mainly because once we consider shear stress, your tau xy is equal to tau yx. So this is equal in terms of magnitude, not necessarily direction. As you know, tau yz, tau zy, and we have tau zx, and that's also tau xz. So magnitudes are equal, but directions are different. So I'm going to write it here. So now we have 6 different different magnitudes. So we have sigma x, sigma y, sigma zz, so or sigma z. So I'm going to flip it here. So we have this and this, but in total we have 9. So those components can be sorry, this can be described by a stress tensor. And what is a stress tensor? So before we discuss a stress tensor, because in a stress tensor, you can describe the plane, the direction, and the magnitude of your stresses. So before we discuss what is stress tensor, let's first determine how can we, for example, quantify, let's say we have pressure or temperature. So let's say we are asked to give a value to pressure or temperature. So normally, if we quantify it, we are given with just one number. So let's say it's let's say 0 degrees Celsius right now, or could be 5 degrees Celsius, or whatever pressure. But normally, this is described by one number or one number. So we can say that, for example, pressure and temperature is a scalar quantity. So that's only described by one number in order for us to describe what's pressure and temperature. And then we can have, for example, velocity. So velocity and let's say heat flux. So if we mention velocity, normally, yeah, you can say it could be scalar, but in reality, if one object is traveling from one position to another position in three-dimensional space, you have to account the movement in terms of x, y, and z, which means this quantities right here could be described by a vector. So the change in x, y, and z axis. So this would be a vector quantity, which is described by three different numbers. Now, for 3D state of stress, it's defined by what we call stress tensor. And in this case, we have 9 different magnitudes or 9 different quantities. So how can we put those numbers right here, those normal stresses, shear stresses, into a stress tensor? So we can write it into a kind of matrix. So your stress, so that would be your stress tensor at a certain point can be described by the following. By the way, we're not going to discuss more about stress tensor, so it's more towards the advanced stress analysis, but I'm just describing how you can kind of make sense all those normal stresses and shear stresses in a 3D state of stress. So now you can write it in a stress tensor in the following way. So you have your normal stresses along the diagonal. You have this tau xy. You have your tau xz. So this is tau yx. This is tau yz. This is tau zx, and this is tau zy. Now, once you see this matrix right here, you would see something in common in terms of, let's say, along the vertical or horizontal direction. So let's take a look, for example, at this direction here. So if we look at this from this point up to this point right here, you can see that the common thing between the three of them is the first subscript right there is x, which means that they are applied on the x face, which is your plane. So this would be along x face. If we go back to our slide, which one is our x face right here? It would be this section right here. So this one up to this one here. So that would be, so you can see x, x, and x. So that's grouped into the same kind of area right here. So same thing here. So that would be for y face, and this would be for z face. Now, how about from top to bottom? If we check from top to bottom, it's also arranged in a systematic way. So you can see the second subscript right here. So x, x, and x, which means that this group right here refers to the x direction in terms of stress. So this would be for x, that would be for y, and that would be for z. Now, if you're working with stress analysis, normally you work with stress tensor, you identify stresses using stress tensor. But for this class, we're going to try to simplify it and not deal a lot with stress tensor. But this is again just showing you how we can kind of make things complicated in terms of 3D state of stress. Now, we mentioned that we are going to first discuss the 2D state of stress. And if we discuss 2D state of stress, we have to assume that sum of the stresses along certain directions is 0. So it's not 3-dimensional anymore. And in this particular case, if we go back to our slide, so we can assume, for example, that our sigma z is equal to 0. We can also assume that everything that has z, so tau yz, so tau xz are all 0, which means we can eliminate this y-axis right here, at least for now, and then do our analysis. So in this particular case, I'm going to turn it again. So So now we are now going to plane stress. Okay, sorry, just checking if you can see it or not. Okay. So we're so for plane stress situation, so which is our 2D, we can assume that our sigma x, or sorry, not sigma, sigma z or zz is equal to tau zy is equal to tau xz, and that would be equal to 0, which means that everything is now in two-dimensional form, which is this slide right here. So now we now eliminate other stresses in other direction, and now it is much more simpler, which looks something like this. So now instead of having three different normal stresses and three shear stresses, now we are left with two normal stress which is sigma x and sigma y, and we are left with only one shear stress, which is tau xy. So now we only have three components instead of 9, so that becomes much more simpler. Now you can even put it into stress tensor if you like. So if you are going to put it into stress tensor or matrix, again, the diagonal of your matrix would be your normal stresses, which is sigma y and sigma x, or you can call it, oh, sorry, it should be the other way, sigma xx and sigma y, and then you can have, for example, this one a tau xy, and then tau xy, and then tau yx. So you can also have that stress tensor, but normally if you talk about stress tensor, it's mostly talking about 3D really, to be honest, but it's more practical to use it for 3D state of stress. Now, by discussing what's the basics in terms of normal and shear stresses, let's go back to our 3D state of stress here. Now, what's the importance of, because in your mechanics of materials 1, you are asked, for example, to determine what would be the equivalent stress at a certain rotated axis. And the thing is, why is that thing important? So let's imagine that, let's say you have a pressure vessel. So you have a container and then it's pressurized inside. And then of course, your container has a certain stress because it's pushing it, for example, towards, so just imagine your soda. Your soda has a certain pressure inside, and of course, there's stresses on the surface of aluminum. Now, why do you need to rotate your stresses? So for example, your container, it's not as smooth as your aluminum can. It could be a pipeline in oil and gas wherein you have welded parts. And what do I mean by welded parts? Imagine that this is a piece of steel. In industry, how they manufacture a pipe is by twisting this piece of plate. So if I twist this one in this way, I would form kind of pipe. And then if you can see it from the video here, so those connections there are being welded. And once they are welded, now you have your pipe, let's say in oil and gas industry. Now, you have welded parts. Most of the time, that's the weakest part when you talk about, let's say, pressure vessels or any type of material. If it's welded, that's the weakest part. And uh, and the way that it works for transformation equation is, let's say if you have welded joints, you want to see what would be the equivalent stress when you are pulling that weld, and then check whether it would fail or not. So that's one practical application of transformation of stresses. So in this case, it's important to have a reference axis and rotated axis. So in this slide right here, you can see that's your reference axis, and that could be your rotated axis wherein you want to determine what would be the stress state at a certain rotation. So this is in three-dimensional, but of course, we have to start with two-dimensional. So we are only dealing with x and y for this particular case. So you can see the rotated axis is x prime, and here it's y prime. Now, as far as I know, you were introduced to these equations here. So how to determine a stress from one point, from a reference axis, which is x and y. So again, we are talking about two-dimensional. And then your x prime would be the stress at a rotated axis. The question here is how these equations were derived. So first, let's look at our 2D state of stress, which is this. Okay, just checking if you can see it. Yeah, you should be able to see it. Okay. So that would be your shear. So now, this would be your y-axis, and this would be your x-axis. So now, so you want to get a stress at a certain rotated position. So in this particular case, let's say we want to rotate it at, for example, from this point here. So let's say that's your, this would be your x-axis. Now, let's say you want to rotate it into this way right here. So let's say you want to get the stresses at that certain rotation. Now, this is sigma x, and then you rotate it at a certain angle. Of course, your y would also rotate, your y-axis. So this would be your, this would be your y prime, and then this would be your x prime. Maybe it's too small, but yeah, I'm just going to change it. So this would be your, okay. So that would be your new y prime. That's your x prime, and this would be your x, and that's your y. So those are the rotated axis. Now, when you talk about stresses, so this initially you have sigma y here, you have sigma x here. Of course, it has to have a component on the other side to make it in equilibrium. So once you have this state, so you want to get what would be the equivalent stress at that's a specific rotated axis. So you want to determine the sigma x prime, and of course, later on, you want to determine what would be the equivalent in sigma y prime. So the way it works is we have to slice our element into this triangular shape. So we take this triangle here. So once we take that triangle, so we have a certain theta right here, which is the amount of rotation that we performed. Now, once we have a theta here, the first thing that we have to think about is, although this is in 2D state, if we go back to our slide, this is actually in 3D that has a certain area. So in reality, what we took is really part of your cube that has a certain area. We can assume that this area right here would be sigma A, or sorry, the delta A. And then this area here, so if this is delta A, if this is your area, that's delta A. This side right here would be delta A sine theta. And you can check it if you want. So this would be delta A cosine theta. So now, again, you slice your cube into this portion. And why did you slice it? Because you want to determine what would be the normal stress acting on that specific plane, because we want to determine our sigma x prime right here. Now, by having our area, and then we have this theta, and then we know that it's a rotated axis. So whatever is being applied on this area right here would be your sigma x prime. So that would be your rotated stress. Now, if we're going to write all the forces acting on this specific in this specific section, so I'm going to write it again in 2D right here. So So this would be the stress that we want, which is sigma x prime. Now we have sigma y right here, which is based on this plot right here. So we have something like a sigma y, so that's sigma y. And then we have sigma x, so we still have sigma x on the other side. So this is sigma x, and that's sigma x right there. So from the top. Now we also have shear stresses applied on our surface. So we have shear stress here, and then shear stress there on this part. And that's from this point right here from the top. Now that's what we call tau xy. Now, once we have this one, so this is rotated by a certain theta angle. Sorry, that's small, but that's a theta angle, which is this guy right here. Now, take note that if we put a reference line here, this sigma x prime is rotated by this amount of theta right there. And now, take note that this is your rotated y-axis. Now I'm going to rewrite it again on the next page so that it's clear, but the idea is to sum the forces along x, along y, and then eventually we are going to come up with this transformation equation. So let's do that quickly. So we have this. I'm going to rewrite it on the next page so that it's clear. So this one. So that section there is. So again, we have theta. And then we have sigma y. This is sigma x. This is tau xy, so you have 2 tau xy there. And then you have the stress that you want to determine, which is x prime. And if you want to know the angle, so that would be theta right there. And take note that once you slice it right there, you will also have tau x prime y prime right there. Now, having these components here, you can now sum forces along x prime, which is equal to, so now when we sum forces, take note they are stresses, they are not forces. So we have to multiply them by their area. So your force is equal to stress times area. Now earlier we discussed, so if I'm going to go back to previous page, we discussed that this would be a delta A, that's delta A sine theta, that's delta A cosine theta, which means I can use those area. So this is delta A. So that's surface there. So that's delta A sine theta. And this is delta A cosine theta. And if we sum the forces along x prime, so take note that your x prime is oriented along your sigma x prime. So that's your rotated axis there. So that's x prime. And then that would be your y prime. Now, if we sum the forces along x prime, what we're going to...
Excuse me, Professor.
Yeah, sorry, go ahead.
Apologies.
Yeah, that's okay.
I understand the basic trigonometry that delta A is obviously the hypotenuse in this case, but I'm not quite sure again what delta A represents in this case. Is it if you go back a previous page, you had drawn the cube cut in half in a way. So does delta A represent that area of that
area?
cut?
Yeah, that's area. So I can...
And it also represents the hypotenuse of the two-dimensional.
Not exactly.
That's what I'm confused about.
Okay, yeah. So we can discuss how this one was taken. So that's okay. So just imagine that. So let's call this one as hypotenuse. And then let's call this one as our, let's say, W. Now, if we're going to take the area of this slice right here, that would be your delta A is equal to HW, right? So that's our assumption right now. Now, if this is H and W, so let's say we take sine of theta. So let's say take the sine of theta is equal to our hypotenuse. Sorry. So let's call this one as B, and let's call this one as A. So right now we have three different dimensions. So we have A, B, and H. Now for this one, if we use sine function, so our sine is opposite, which is B divided by H, right? So in this particular case, so our B is equal to H sine of our theta, right? Which means if I'm going to take the area right here underneath, which is where my stress is, that would be W times B, right? Which in this case, that's W times H sine theta. So my area is equal to W times B. And my B is actually H sine theta. So which means that my W is W times H sine theta. Now take note, your WH is equal to delta A, which means this area right here is equivalent to delta A sine theta. So did you get that?
It makes it it's clarified it a little bit. I think just
Okay.
additional time to review it should help. But thank you, Professor, for clarifying
Okay, no
that.
problem. Yeah, if you have any questions about anything, just feel free to ask. So I really appreciate that, especially that we don't have much interaction. I really appreciate any question, to be honest. So yeah, thank you. Yeah, any questions about taking out the area right here? So it's just a matter of playing with your trigonometry. So again, you can play with that and you'll be able to see that if you assume that this is delta A, this would be delta A sine theta, and that would be delta A cosine theta. Yeah, clear? Yeah, and thanks for that question. And yeah, question clear? Okay. Now let's move on. So now we have now all the forces in this diagram here, wherein we take a cut at a certain rotated axis because we want to take the equation from there, right? So now we can sum forces along our rotated axis, which is x prime, but these are stresses, these are not forces. So again, that's why we need to use this equation here. So we have stress times our area. So now, if we are going to sum the forces along x prime, so first let's take a look at this x prime right here, or delta x prime. Oh, sorry, sigma x prime. So our sigma x prime is applied to this section here, which is our diagonal. And our diagonal has an area of delta A. Now, our delta A is this, so that's your stress applied to that specific area. So that would be associated with this delta x prime. Oh, sorry, a sigma x prime. I'm just looking if I have a different color of marker. I think next time I'm going to bring a different color so that you can see it properly. But yeah, so now we have sigma x prime. Now, the next thing is let's look at this sigma x. So again, sigma x, and then you have to multiply it to its area. So sigma times its area, but we have to orient it to our new axis, which is x prime, which means that for this sigma x, so it's pointing to the negative side of this axis. So take note that if we assume that that's our positive direction, so this is pointing towards the negative direction in our x prime, which means that this would be a negative sigma x, and then we have our area, which is delta A cosine of our theta. So that's the area right here. So that's your area. And this is not yet aligned to your x prime. So you have to multiply it to your cosine angle, which means that this would be cosine theta. Now you have to do it one by one. I'm going to write it right now. You can do a little bit of practice, but I'm going to write it one by one right now. So we considered this sigma x. Now we have sigma y. Sigma y is pointing to the negative direction of your x prime direction. And that would be negative sigma y. So that's sigma y applied to that area. So which means to take my forces, I need to multiply it to this area right here. So that's delta A sine of your theta, and then sine of your theta right here. So you resolve it to this to this side right here. That makes it sine right there. We're going to don't worry about derivation. There's no derivation in your exam, but I want for you to see that those equations would make sense, and you should know how those equations were derived. So that's sine theta. Now that's your sigma y. How about your shear stresses right here? So your shear stresses is, so in this case is negative tau xy is delta A cosine of your theta. So again, we started from this side. Take note, you have two shear stresses applied to this side and applied on this side right here. So tau xy, so we start with this side here, and then times sine of our theta to resolve it along x prime axis. And then we have minus tau xy. Now we are on this side right now. So tau xy delta A sine of our theta. So that's just your area, and then cosine of your theta, and that would be equivalent to 0. So that's our first equation there. Now, of course, if you look at where's tau x prime, y prime, of course, that would not contribute to the stresses associated with x prime. Now, we have first equation. How about the second equation? The second equation is summation of forces along our y prime axis, which means that your y prime axis is this rotated axis here. So that would be your y prime. Now, if that's your y prime, so we start with x again, or what's the contribution of sigma x, sigma y, and everything, and this would be the following. So your sigma x would be, sigma x, so this one right here, sigma x is equal to delta A cosine of our theta, which is our area, sine of our theta. So now we move to our sigma y. So minus sigma y. Okay, so take note that this would be the positive direction, and this would be the negative direction. So your x is pointed towards on the positive side for this axis here. Now, if we write it down, that would be delta A sine of theta cosine of your theta. So that's for this guy right here. Now we have this component contributing to our stress, which is in a positive direction. So that's tau x prime y prime, and that the area is delta A. So that's positive. And then we move on to our shear stresses. So we have two different shear stresses. So the one is in positive direction, one is in negative direction. So you can see this one is towards positive y prime, and this one is towards negative. So let's start with -1, which is this guy right here. So our negative is, I'm thinking if we can see it, yeah, negative tau xy. I'm going to rewrite it on the next page. So delta A cosine of our theta. So now that's the area right there, cosine of theta. And then for the positive one, I'm going to move the paper here. I'm not sure if you can see it, but for the positive one, it would be plus tau xy delta A. I'm going to move the paper later if you can't see it. Sine theta is equal to 0. I'm going to rewrite the equations later, but that would be the equation there. So we have contributions from x, so y, tau x prime y prime, negative tau xy, and then positive tau xy. So we just sum forces along x prime and y prime. Now, once we sum those forces, so I'm going to rewrite it here. So, okay, so we have, okay, so maybe instead of rewriting it, I'll just combine some of them. So I'm going to show it again, sorry, because we only have 3 minutes. So instead of writing it for 3 minutes, so, okay, I'm just checking if you can see it. So again, this is negative tau xy. That's positive tau xy, this one, and that's a delta A sine theta times sine theta up there, and then that's equivalent to 0. Now, if we are going to simplify this equation, and we can go back to that next meeting, but if we simplify that one, your summation of fx 0, so that would be equal to x prime is equal to sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy sine theta cosine of theta. So that's for x prime axis. And for our y prime axis, which is equivalent to 0, what we got is tau x prime tau x prime y prime, and that's equivalent to negative sigma x minus sigma y sine of theta cosine of theta plus tau xy cosine squared theta minus sine squared theta. And take note that these numbers right here, we just simplified the things that we added from this previous notes right here. So we just simplified this numbers right here into this form. Nothing fancy. We just added what we can add, what we can subtract, and then we got this two equations. Now, once we get this two equation, we can apply. So if we look at this equation, we have cosine squared, we have sine squared, we have this. So we have this relationship here, this relationship here. We can simplify it by applying some of the trigonometric relations. So let's say if we talk about for example, sine 2 theta is equal to 2 sine theta cosine of theta. So I'm just writing some of the trigonometric relationship that you learn from your trigonometry, I hope. Sine squared theta, 1 minus cosine 2 theta divided by 2. So we just substitute, for example, this sine 2 theta, we have 2 sine theta cosine theta, and we can see that we have it up here. And then we have cosine squared theta is equal to this relationship here. And then we have cosine squared there. We have sine squared right there. And then same thing here, we have sine square. We have this following relation. So we have sine square, for example, right here. And then once we apply or once we substitute those numbers, you will end up with this equations here. So for example, sigma, so I'm going to show it to you. Or yeah, it's already 2:21. I can stop here for now. I'm going to show you next meeting that once we substitute this trigonometric relationships here into this equations from summation of x prime and then y prime, you will end up with the these equations here on the slide. Any questions, class, before we move? So I'm just going to check the